Group Technology and Cellular Manufacturing Engg. Ahmed Al-Afifi. What is Group Technology, GT? GT is a theory of management based on the principle that similar things should be done similarly. GT is the realization that many problems are similar, and that by grouping similar problems, a single solution can be found to a set of problems, thus saving time and effort. GT is a manufacturing philosophy in which similar parts are identified and grouped together to take advantage of their similarities in design and production. Implementing GT. Where to implement GT? Plants using traditional batch production and process type layout. If the parts can be grouped into part families. How to implement GT? Identify part families. Rearrange production machines into machine cells. Types of layout. In most of today's factories it is possible to divide all the made components into families and all the machines into groups, in such a way that all the parts in each family can be completely processed in one group only. The three main types of layout are line, product, layout, functional layout, group layout. Line, product, layout. It involves the arrangements of machines in one line, depending on the sequence of operations. In product layout, if there is more than one line of production, there are as many lines of machines. Line layout is used at present in simple process industries, in continuous assembly, and for mass production of components required in very large quantities. Functional layout. In functional layout, all machines of the same type are laid out together in the same section under the same foreman. Each foreman and his team of workers specialize in one process and work independently. This type of layout is based on process specialization. Group layout. In group layout, each foreman and his team specialize in the production of one list of parts and cooperate in the completion of common tasks. This type of layouts based on component specialization. The difference between group and functional layout. Identifying part families. Large manufacturing system can be decomposed into smaller subsystems of part families based on similarities in 1. Design attributes and 2. Manufacturing features. Identifying part families. Design attributes. Part configuration, round or prismatic. Dimensional envelope, length to diameter ratio. Surface integrity, surface roughness, dimensional tolerances. Material type. Raw material state, casting, forging, bar stock, etc. Identifying part families. Part manufacturing features. Operations and operation sequences, turning, milling, etc. Batch sizes. Machine tools. Cutting tools. Work holding devices. Processing times. Identifying part families. Group technology emphasis on part families based on similarities in design attributes and manufacturing. Therefore GT contributes to the integration of CAD and CAM. Part families. A part family is a collection having similar. Three methods for identifying parts families. Visual inspection. Classification and coding. Production flow analysis. Forming part families. 1. Visual inspection method. Forming part families. 1. Visual inspection method. Incorrect results. Human error. Different judgment by different people. Inexpensive. Least sophisticated. Good for small companies having smaller number of parts. Forming part families. 2. Classification and coding. The process of assigning symbols to the parts. Where the symbols represent design attributes of parts, manufacturing features of parts, or both. Classification. The process of categorization of a set of parts into part families. Forming part families, classification and coding. A GT code is a string of characters capturing information about an item. Three main types of coding systems: structure, monocode or hierarchical structure, polycode or chain type structure, mixed mode structure, monocode. Monocode. A monocode, hierarchical code, provides a large amount of information in a relatively small number of digits. Useful for storage and retrieval of design-related information such as part geometry, material, size, etc. It is difficult to capture information on manufacturing sequences in hierarchical manner, so applicability of this code in manufacturing is rather limited. Polycode. The code symbols are independent of each other. Each digit in specific location of the code describes a unique property of the workpiece. It is easy to learn and useful in manufacturing situations where the manufacturing process have to be described. The length of a polycode may become excessive because of its unlimited combinational features. Polycode. Polycode. Mixed mode, the Opitz classification system. It is a mixed, hybrid, coding system. Developed by Opitz, Technical University of Aachen, 1970. It is widely used in industry. It provides a basic framework for understanding the classification and coding process. It can be applied to machine parts, non-machine parts, both formed and cast, and purchased parts. It considers both design and manufacturing information. Mixed mode. Form code. Focus on part geometry, dimensions and features relevant to part design. Supplementary code. Includes information relevant to manufacturing, such as raw material, tolerance, and surface roughness. Secondary code. Intended to identify the production operation type and sequence. It can be designed by the user firm to serve its own needs. Basic structure of the Opitz. Basic structure of the Opitz system. Form code, digits 1 to 5. The form code in the Opitz system is 15,100. Example, Opitz part coding system. Given the rotational part design below, determine the form code in the Opitz parts classification and coding system. Solution. Length to diameter ratio, LD equals 1.5, digit 1 equals 1. External shape, both ends stepped with screw thread on one end, digit 2 equals 5. Internal shape, part contains a through hole, digit 3 equals 1. Plane surface machining, none, digit 4 equals 0. Auxiliary holes, gear teeth, etc., none, digit 5 equals 0. The form code in the Opitz system is 15,100. Example. Part class. Rotational part, LD equals 9. 9/4.82.0 based on the pitch circle diameter of the gear, so the first digit equals 1. External shape. The part is stepped on one side with a functional groove, so the second digit is 3. Internal shape. The third digit is 1 because of the through hole. Plane surface machining. The fourth digit is 0 because there is no plane surface machining. Auxiliary holes and gear teeth. The fifth digit is 6 because there are spur gear teeth on the part. Forming part families, classification and coding, production 3. Forming part families, classification and coding, production 3. Flow analysis, PFA. PFA is a method for identifying part families and associated machine groupings based on the required manufacturing processes need for each part. Selection of classification and coding systems. Define your objectives, reasons and users. Try to get consensus so that the classification and coding system is useful in design, purchasing, manufacturing, quality, etc. Robustness and expandability. Can it work with the current product and accommodate unknown future products and applications? Automation and efficiency. Is it easy to get information in and out in a timely manner, And is the coding system able to handle present and future products? Simplicity and user interface. Will people use it? Cost. As an engineering decision with far-reaching impact, what's the true cost? Benefits of group technology. It affects all areas of a company, including engineering, equipment specification, facilities planning, process planning, production control, quality control, tool design, purchasing, service. Benefits of group technology. Some of the well-known tangible and intangible benefits of implementing GT. Engineering design. Reduction in new parts design. Reduction in the number of drawings through standardization. Reduction of number of similar parts, easy retrieval of similar functional parts, and identification of substitute parts. Benefits of group technology. 2. Layout planning. Reduction in production floor space required. Reduced material handling effort. Benefits of group technology. 3. Specification of equipment, tools, jigs, and fixtures. Standardization of equipment. Implementation of cellular manufacturing systems. Significant reduction in upfront costs incurred in the release of new parts for manufacture. Benefits of group technology. 4. Manufacturing, process planning. Reduction in setup time and production time. Alternative routing leading to improved part routing. Reduction in number of machining operations and numerical control, North Carolina, programming time. Benefits of group technology. 5. Manufacturing, production control. Reduced work in process inventory. Easy identification of bottlenecks. Improved material flow and reduced warehousing costs. Faster response to schedule changes. Improved usage of jigs, fixtures, pallets, tools, material handling, and manufacturing equipment. Benefits of group technology. 6. Manufacturing, quality control. Reduction in number of defects leading to reduced inspection effort. Reduced scrap generation. Better output quality. Increased accountability of operators and supervisors responsible for quality production, making it easier to implement total quality control concepts. Benefits of group technology. 7. Purchasing. Coding of purchased part leading to standardized rules for purchasing. Economies in purchasing possible because of accurate knowledge of raw material requirements. Reduced number of part and raw materials. Simplified vendor evaluation procedures leading to just-in-time purchasing. Benefits of group technology. 8. Customer service. Accurate and faster cost estimates. Efficient spare parts management, leading to better customer service. Lower lead times. Cellular manufacturing is an application of group technology in manufacturing in which all or a portion of a firm's manufacturing system has been converted into cells. A manufacturing cell is a cluster of machines or processes located in close proximity and dedicated to the manufacturing of a family of parts. Why cellular manufacturing? Reduce setup times by using part family tooling and sequencing. Reduce flow times by reducing setup and move times and wait time for moves and using smaller batch sizes. Reduce inventories. Reduce lead time. Cell design. Design of cellular manufacturing system is a complex exercise with broad implications for an organization. The cell design process involves issues related to both system structure, structural issues, and system operation, procedures issues. Cell design structural issues include selection of part families and grouping of parts into families, selection of machine and process populations and grouping of these into cells, selection of tools, fixtures, and pallets, selection of material handling equipment, choice of equipment layout, cell design, detailed design of jobs. Procedures issues include detailed design of jobs, organization of supervisory and support personnel around the cellular structure, formulation of maintenance and inspection policies, design of procedures for production planning, scheduling, control, and acquisition of related software and hardware, modification of cost control and reward systems, outline of procedures for interfacing with the remaining manufacturing system, in terms of workflow and information, whether computer-controlled or not, evaluation of cell design decisions. The evaluation of design decisions can be categorized as related to either the system structure or the system operation. Evaluation of cell design decisions. Typical considerations related to the system structure include equipment and tooling investment, low; equipment relocation cost, low; material handling costs, low; floor space requirements, low; extent to which parts are completed in a cell, high; flexibility, high. Evaluation of cell design. Evaluations of cell system design are incomplete unless they relate to the operation of the system. A few typical performance variables related to system operation are equipment utilization, high; work in process inventory, low; queue lengths at each workstation, short; job throughput time, short; job lateness, low. Cell formation approaches. 1. Machine component group analysis. Machine component group analysis is based on production flow analysis. Machine component group analysis. Production flow analysis involves 4 stages. Stage 1. Machine classification. Machines are classified on the basis of operations that can be performed on them. A machine type number is assigned to machines capable of performing similar operations. Production flow analysis involves 4 stages. Machine component group analysis. Production flow analysis involves 4 stages. Stage 2. Checking parts list and production route information. For each part, information on the operations to be undertaken and the machines required to perform each of these operations is checked thoroughly. Production flow analysis involves 4 stages. Machine component group analysis. Production flow analysis involves 4 stages. Stage 3. Factory flow analysis. This involves a micro-level examination of flow of components through machines. This, in turn, allows the problem to be decomposed into a number of machine component groups. Production flow analysis involves 4 stages. Machine component group analysis. Production flow analysis involves 4 stages. Stage 4. Machine component group analysis. An intuitive manual method is suggested to manipulate the matrix to form cells. However, as the problem size becomes large, the manual approach does not work. Therefore, there is a need to develop analytical approaches to handle large problems systematically. Machine component group analysis. Example: consider a problem of 4 machines and 6 parts. Try to group them. Components. Machines 1, 2, 3, 4, 5, 6, M1, M2, M3, M4. Machine component group analysis. Solution. Components. Machines 2, 4, 6, 1, 3, 5, M1, M2, M3, M4. Rank order clustering algorithm. Rank order clustering algorithm is a simple algorithm used to form machine part groups. Rank order clustering algorithm. Step 1. Assign binary weight and calculate a decimal weight for each row and column using the following formulas. Rank order clustering algorithm. Step 2. Rank the rows in order of decreasing decimal weight values. Step 3. Repeat steps 1 and 2 for each column. Step 4. Continue preceding steps until there is no change in the position of each element in the row and the column. Rank order clustering algorithm. Example: consider a problem of 5 machines and 10 parts. Try to group them by using rank order clustering algorithm. Table 1. Components. Machines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, M1, M2, M3, M4, M5. Rank order clustering algorithm. Binary weight. Table 2. 29, 28, 27, 26, 25, 24, 23, 22, 21, 20. Components. Machines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Decimal. Equivalent. M1. 1007. M2. 451. M3. 568. M4. 455. M5. 1020. Rank order clustering algorithm. Table 3. Binary weight. 29, 28, 27, 26, 25, 24, 23, 22, 21, 20. Components. Binary weight. Machines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 24, M5, 23, M1, 22, M3, 21, M4, 20, M2. Decimal. Equivalent. 28, 27, 26, 11. Rank order clustering algorithm. Binary weight. Table 4. 29, 28, 27, 26, 25, 24, 23, 22, 21, 20. Components. Binary weight. Machines. 1, 5, 7, 2, 3, 4, 8, 6, 9, 10. Decimal. Equivalent. 24, M5, 1020, 23, M1, 1019, 22, M3, 900, 21, M4, 123, 20, M2, 115, 28, 27, 26, 11. Rank order clustering algorithm. RO clustering oscillations indicating need of machine replication happens often. Presence of outliers and or voids in the finished clusters. Outliers indicate the need of machine replication. Voids indicate skipped machines in a cell. Generally speaking, these clustering algorithms are designed to convert existing routes for facility reorganization. They require a previous engineering study to be performed to develop a series of routers on a core sample of parts that represent most of the production in the shop. Rank order clustering algorithm. The ROC provides a simple analytical technique that can be easily computerized. The ROC has fast convergence and relatively low computation time depending on the matrix size. The fact that ROC uses binary values will impose restrictions on the size of the matrix that can be solved. Rank order clustering algorithm. Most computers have a maximum of 248 to 1 for integer representation, which means that the maximum number of rows and columns is limited to 47 and columns is limited to 47. The algorithm results depend on the initial matrix arrangement. The algorithm collects positive entries, ones, in the top left-hand corner, leaving the rest of the matrix disorganized. Cluster identification algorithm, CIA. Designed to identify disconnected blocks if they exist. If there are no disconnected blocks, the matrix is not mutually separable. The entire matrix will form one block. The algorithm begins by masking all columns that have an entry of 1 in any row, selected randomly, then all rows that have an entry of 1 in these columns are masked. This process is repeated until all intersecting columns and rows are masked. Cluster identification algorithm, CIA. These masked columns and rows are placed in a block and removed from the matrix. Then the process of masking starts again and another block is identified. This will continue until all the entries in the matrix are assigned in blocks and all separable blocks are identified. Cluster identification algorithm, CIA. Example. Step 1. Select any row I of the incidence matrix and draw a horizontal line high through it. Row 3 of the matrix is selected randomly and a horizontal line H3 is drawn. Cluster identification algorithm, CIA. Step 2. For each entry of 1 crossed by the horizontal line H3, draw a vertical line VJ. 3 vertical lines V2, V6, and V7 are drawn. Cluster identification algorithm, CIA. Step 3. For each entry of 1 crossed once by a vertical line VJ, draw a horizontal line. A horizontal line H6 is drawn through all the crossed once entries of the matrix. Cluster identification algorithm, CIA. Step 4. The preceding steps are repeated until no more crossed once entries are left. All the crossed twice entries are grouped in a block and removed from the matrix. Parts 2, 6, 7 and machines 3, 6 are grouped in one block. Cluster identification algorithm, CIA. The grouped parts and machines are removed from the matrix. Cluster identification algorithm, CIA. Step 5. The above procedure is repeated for the remaining matrix entries until all entries are grouped. Cluster identification algorithm, CIA. The resulting matrix is as follows. Arranging machines in a GT cell. After part machine grouping have been identified by cell formation approaches, the next problem is to organize the machines into the most logical arrangement. Hollier method. This method uses the sums of flow from and to each machine in the cell. The method can be outlined as follows. Develop the from to chart from part routing data. The data contained in the chart indicates numbers of part moves between the machines in the cell. Determine the from and to sums for each machine. This is accomplished by summing all of the from trips and to trips for each machine. The from sum for a machine is determined by adding the entries in the corresponding row. The to sum is found by adding the entries in the corresponding column. Arranging machines in a GT cell. Assign machines to the cell based on minimum from or to sums. The machine having the smallest sum is selected. If the minimum value is a to sum, then the machine is placed at the beginning of the sequence. If the minimum value is A from sum, then the machine is placed at the end of the sequence. Tiebreaker. If a tie occurs between minimum to sums or minimum from sums, then the machine with the minimum from /to ratio is selected. If both to and from sums are equal for a selected machine, it is passed over and the machine with the next lowest sum is selected. If a minimum to sum is equal to a minimum from sum, then both machines are selected and placed at the beginning and end of the sequence, respectively. Reformat the from to chart. After each machine has been selected, restructure the from to chart by eliminating the row and column corresponding to the selected machine and recalculate the from and to sums. Repeat steps 3 and 4 until all machines have been assigned. Example of arranging machines in a GT cell. Suppose that 4 machines, 1, 2, 3, and 4 have been identified as belonging in a GT machine cell. An analysis of 50 parts processed on these machines has been summarized in the from to chart presented below. Additional information is that 50 parts enter the machine grouping at machine 3, 20 parts leave after processing at machine 1, and 30 parts leave after machine 4. Determine a logical machine arrangement using Cellular method. Example of arranging machines in a GT cell. First iteration. Example of arranging machines in a GT cell. Second iteration with machine 3 removed. Example of arranging machines in a GT cell. Third iteration with machine 2 removed. The resulting machine sequence 3214. Example of arranging machines in a GT cell. The flow diagram for machine cell in the example is shown below. Flow of parts into and out of the cells has also been included. Cellular method. Cellular method.